Welcome to the Center for Subsurface Energy and Environment webinar series. My name is Matt Balhoff. I am the director of the center and a professor in the Hildebrand Department of Petroleum and Geosystems Engineering. To learn more about all the research that we're doing and ways that you can collaborate, please visit our website. The center includes 24 principal investigators, mostly faculty in the Petroleum and Geosystems Engineering, as shown here. We work on a number of subsurface applications, technical disciplines, and use many different engineering tools. We collaborate with industry in a lot of different ways. One of them is through industrial affiliates projects. I highlighted one at the bottom here. This is a brand new industrial affiliates project that we're putting together on carbon utilization, storage, and transportation. Today's speaker, Dr. Okunu, is a co-lead for this new IAP. These webinars are informative, industry-driven webinars by researchers and collaborators in the center. They're usually the first Friday of the month at 12 p.m. via Teams. All webinars are uploaded to the YouTube channel that we have, but we do encourage you to attend them live so that you can ask questions. The next webinar will actually not be the first Friday of the month due to the July 4th holiday. Instead, it'll be Friday, July 9th. That's going to be a little bit different, hopefully a little bit different format than our usual webinar. So we are looking at potentially putting together a panel discussion on CCUS and particularly the new Carbon UT IAP. So if you're interested in that at all, please attend. That panel will include Dr. Nicolas Espinoza, Dr. Okunu as well, actually, and maybe a couple of others. And so here's a little a bit about that new IAP that we'll talk about next month. If you're interested, then please do send us an email. With that, I would like to introduce today's speaker, and that is Dr. Ryosuke Okunu. He holds a BE and an ME degrees in Geosystems Engineering from the University of Tokyo, and he holds a PhD degree in Petroleum Engineering from the University of Texas at Austin. He is now a faculty member at UT PGE, but prior to that, he served as assistant professor of Petroleum Engineering at the University of Alberta. He also has 7 years of industrial experience as a reservoir engineer and as a registered PE in Alberta, Canada. His research and teaching interests include enhanced oil recovery, heavy oil recovery, unconventional and gas resources, numerical simulation, thermodynamics, multi-phase behavior, and applied mathematics, and of course, CCUS. So with that, I'm going to turn it over to Dr. Okunu, and I'd like to remind you that if you have any questions at any time, you can submit those in the chat. And at the end of the talk, Dr. Okunu will attempt to answer some of those questions. So thank you, and I'll turn it over to Ryosuke.
Okay, great. Well, thank you very much for the introduction, Dr. Balhoff. Hello, everyone. I'm Ryosuke Okunu, Associate Professor of Petroleum Engineering at the University of Texas at Austin. And I'm going to present the novel wettability modifiers for enhanced oil recovery today. So we have worked upon this research on wettability alteration over the past 5 years, starting with the conventional carbon reservoirs, and then we extended the program to the application in shale and tight reservoirs. So here I'm showing key technical contributors to the research program, and I'm going to give a talk on their behalf today, and especially the large fraction of the material I'm going to cover today is based upon the PhD studies by Dr. Mingyong Wang. I believe he's one of the audience today. So here's the outline for the presentation. So first, I'm going to discuss motivation for development of wettability modifiers for carbon reservoirs, and then the transition to the application to shale and tight formations. And this presentation explains some details of our thought process that led to a novel wettability modifier, which is a ketone solvent. So I will then explain research objectives, followed by key results and next steps for the ketone solvent research. So carbon reservoirs hold 60% of world oil reserves, but they are often difficult for water flooding to efficiently recover oil because the interval displacement of oil by water tend to bypass the oil residing in rock matrix. So number one reason for that is the permeability contrast between the rock matrix and the fracture network. The recovery from rock matrix is more difficult when the reservoir rock is oil wet. So this figure shows that the ultimate recovery factor is smaller when covered the rock is more oil wet based upon the actual field data. So as shown in this schematic, water tend to channel through the fracture volume and bypass a rock matrix. In this situation, oil recovery from matrix relies on the water imbibition into the matrix that expel the oil from there. So this water imbibition into the matrix is more difficult when the rock matrix is oil wet. Therefore, the use of wettability alteration agent has been studied for enhancing water imbibition in carbonate reservoirs that are often naturally fractured. So low salinity water is widely studied for that purpose, in which the polar interaction between sulfate and the rock surface helps alter the wettability of rock. And the surfactant solution has been also studied, which release oil from the rock surface also. However, the researchers pointed out that reduced IFT by surfactant solution tend to limit the imbibition rate. So therefore, we studied the new classes of wettability modifiers that are not surface active as part of the research program. So we started by investigating what makes low salinity water effective in enhancing water imbibition in carbonate reservoirs. And the main species in the mechanism of wettability alteration in this case is sulfate. So we investigated many polar species that may act in a similar way to sulfate in low salinity water. And one of them is amino acid as shown here. In particular, we studied the simplest amino acid, which is glycine, and published a series of papers on this. And also we are studying carboxylates as a wettability modifier, partly because we wanted to see the role of amino group of amino acid on wettability modification by comparing the amino acid and carboxylates. In particular, the simplest carboxylate formate is what we are actively investigating these days. So this simplest carboxylate is interesting because we can make a formate from CO2 and water by electrochemical reaction. So if we can make a formate or formic acid by using a captured CO2 and water, that will be a novel, effective way to store CO2 in a geological formation. So right now, gaseous CO2 injection is essentially the only way to make EOR carbon negative, but it's possible to make even water flooding carbon negative if we use the formate as wettability modifier in water flooding. So I may be able to give more details on carboxylates in the context of carbon storage in the coming webinar in July. So these are all polar components that are in general not soluble in water, not soluble in oil. So we studied a novel class of wettability modifiers that is less polar, which is the oxygenated solvent, and for example, ketone solvents. And in particular, we studied 3-pentanol, the symmetric short ketone, in detail over the past few years. And today, we are going to focus upon the 3-pentanol as a novel wettability modifier, especially effective for tight shale formations. So now, when we consider the application of wettability modifiers to tight and shale formations, there are additional factors that affect the design of wettability alteration. As you know, the oil production in tight and shale formation often show rapid decline within a few years, and therefore primary depletion, resulting in oil recovery factors below 10%. So it's important to consider EOR methods that increase oil production without having to drill many new wells. So gas injection has been studied and implemented, but it comes with expensive operations of gas compressors and gas processing. So rapid decline in oil production comes, of course, from extremely low permeability of shale and tight formations. This also means that the pores in unconventional reservoirs are much smaller than the conventional oil reservoirs. Therefore, interaction between fluid and rock surface is more important in oil production from shale tight formations. And many shale plays show the oil wet or mixed wet state as presented in the literature. So water-based EOR is a good option to carry polar chemicals that affect the rock wettability, unlike gas injection, which is basically polar, a non-polar fluid injection. So however, cyclic injection or half and puff of aqueous solution require much more rapid response of oil production in comparison to water flooding in conventional reservoirs. So wettability modifiers that I mentioned in the previous slide are highly polar, therefore they wouldn't go into the oil phase or oil layer on the rock surface. So we hypothesize that the polar solvent can improve oil recovery from tight and shale formation more than conventional polar wettability modifiers. So it's a solvent miscible with oil and slightly soluble in water. So when it is injected as part of water, it can transfer from water phase to oil phase, and therefore they can access the rock surface through both phases, releasing oil from there. Also, the affinity of the chemical to oil makes it more rapid to transfer from fracture to the matrix, therefore to expel oil from there more efficiently. So these are the thought process behind the hypothesis. And this slide summarizes what we looked for in the spectrum of polarity for wettability modifiers. So low salinity water injection relies mainly on sulfate, which is highly polar, and surfactant have two characteristics within the molecule, hydrophobic tail and hydrophilic head. And we asked the question, is there any solvent that can alter the rock wettability on this less polar side, expecting more rapid oil production response in half and puff operation? And in particular, we studied solvent with separation of charge, for example, ketones, and also alcohol. So we studied many polar solvent in the initial stage of research, and dipole moment is used to parameter that quantifies the component's polarity. So this slide shows the dipole moments of some alcohol and one ether, DME. So they range from 1.3 to 1.7. And here I'm showing the dipole moments of ketones. They are much greater than the values shown in the previous slide. From this list, we found that acetone was actually a good wettability modifier based upon experimental data, but it made a viscous oil phase in the presence of oil, water and oil. So we took a balance between the affinity to oil and affinity to water. And as a result, we found the 3-pentanol is the most promising ketone solvent as a wettability modifier. So the large dipole moment of ketones come from this carbonyl oxygen that is electron rich. Therefore, it reduces the interaction between rock surface and the polar oil component. And 3-pentanol is a short symmetric ketone with the chemical structure shown here. It's widely used in the food industry and commercially available at a low cost. And its volatility is similar to normal heptane as shown here in this PT diagram. Vapor pressure of 3-pentanol is compared with vapor pressure curves for N-alkane series. So it's possible to inject 3-pentanol as part of injection gas, but in this presentation, we are focused on the result using aqueous solution of 3-pentanol. So for example, we used it as part of formation brine in many experiments. So it's miscible with oil and slightly soluble in water. So this particular brine used in this research can contain 1.1 weight percent 3-pentanol at the reservoir temperature 374 Kelvin. So this snapshot on the right side shows a stability test of 3-pentanol in this particular reservoir brine at the reservoir temperature. So at the concentrations above 1.1 weight percent, 3-pentanol makes its own phase, 3-pentanol rich phase, along with a quite a stable brine phase below. So this 3-pentanol rich phase works as a miscible solvent, but today's presentation is focused on the 3-pentanol as part of reservoir brine at approximately 1%. So this is a excess 3-pentanol rich phase, and phase below is a water phase that contains 3-pentanol. And this shows solubility limit of 3-pentanol is smaller than the stability limit of this brine. So it's we are studying about 1% concentration of 3-pentanol in the brine as an injectant. So we have published a series of papers on 3-pentanol, and so in this today's talk, because we have a limited amount of time, I'm going to highlight the key results only. The first, I'd like to show how 3-pentanol can change rock wettability without affecting the interfacial tension between water and oil, unlike surfactant. And then after that, I'm going to show comparison between surfactant and the 3-pentanol in dynamic inhibition experiment. The way we performed the experiment, this dynamic inhibition experiment, allowed us to study details of mass transfer between fraction matrix. So we were able to see the key differences between 3-pentanol and surfactant as wettability modifier. After that, I'm going to show result of half and a puff experiment using the shale cores with a realistic injection brine based upon field data. So in what follows, we are going to discuss two types of experiment. The first one is performed to compare surfactant and 3-pentanol, and also to see the details of mass transfer using a fractured core. And second one is half and puff experiment using shale cores. So we studied 3-pentanol using oil sample from Texas shale play. The reservoir brine salinity for this case is around 69,000 ppm with approximately 150, 100 ppm of divergent cations, calcium and magnesium. And as I showed previously, the solubility of 3-pentanol in this brine is 1.1 weight percent at the reservoir temperature of 347 Kelvin. So it's a small amount of 3-pentanol in the injection brine. So first, I'm showing here the contact angle experiment for the two cases, one with the reservoir brine alone, and the other with the 3-pentanol solution in the brine at the solubility limit 1.1 weight percent. So contact angle for the brine case is greater than 120 degrees after several days, confirming the surface is oil wet. With a 3-pentanol solution here, contact angle rapidly reduced to 20 degrees only after 2 days. And 3-pentanol is not surface active, so why does it work so fast as a wettability alternation agent? And possible explanation is that the 3-pentanol is much more soluble in oil than in water. So there's a mass transfer of 3-pentanol from a water phase to oil phase, and the 3-pentanol is expected to interact with rock surface from both phases, water and oil, and finally release oil from rock surface. So we confirmed the wettability alternation by a small amount of 3-pentanol in the brine. And next, we wanted to see the impact of 3-pentanol on oil-water interfacial tension. In this particular case, the crude oil reservoir brine IFT with no chemical have an IFT of 11 dyne per centimeter, and with the addition of 3-pentanol, it didn't show any meaningful change from the original value. So we confirmed that wettability change by 3-pentanol was occurring without affecting interfacial tension. Now let's see how 3-pentanol solution can enhance water imbibition in coagulate. But before that, I'm here introducing a surfactant we used as a counterpart in this part of presentation. So we used 2-ethylhexanol 4-PO EO, which is non-ionic surfactant with a very short hydrophobe. So we confirmed that it rapidly changed the contact angle on oil-aged calcite surface from initial 134 degrees to 47 degrees within a day. So it's equivalent to 3-pentanol as a wettability modifier. But please note that IFT is reduced to 0.2 dyne per centimeter, unlike the 3-pentanol case. So these two species are going to be compared. So 3-pentanol and the 2-ethylhexanol 4-PO15-EO. And I'm summarizing the key characteristics of these two species here. And they are equivalent as a wettability modifier, as I showed in the previous slide. But the 3-pentanol does not change the water-oil interfacial tension, while surfactant reduces it to 0.2 dyne per centimeter. And the 3-pentanol is miscible with the oil and slightly soluble in brine. So that makes a strong mass transfer when 3-pentanol solution is in contact with the oil. And 3-pentanol seems to be cheaper than surfactant in general. So dynamic imbibition experiment used an oil-aged limestone cores with a fracture as shown in this schematic and the photo. The fracture permeability was much greater than the matrix permeability, and in this experiment, IFT wasn't affected by the presence of 3-pentanol, and the oil recovery in this flow configuration is still a capillary dominant process. It's unlikely that the pressure gradient caused a meaningful cross-flow during this particular experiment. So experiment started by reservoir brine injection. It was continued until no more oil was produced. And then the chemical slug, either 3-pentanol or surfactant, was injected for 1.6 pbi, per volumes injected, which is approximately 24 hours. And the residence time in the fracture volume was approximately 14 minutes. After that, chase brine was injected. So here's the result. So reservoir brine flooding recovered only 70% for the both cases. And 3-pentanol cases rapidly increased oil production in the slug injection stage. And after stopping the slug injection, the only brine injection recovers some additional oil because wettability of rock had been changed by the slug injection. And please note that the oil recovery factor for this 3-pentanol case has been corrected for the solubility of 3-pentanol in the produced oil. In the surfactant case, also increased oil recovery in this slag stage, and also after switching to straight chase brine injection, the additional oil recovery was observed. And the final oil recovery was similar to each other in this case, but both didn't reach ultimate oil recovery, so it wasn't compared. And although not shown in this presentation, we have published a detailed mass transfer of the chemicals and water between fracture and matrix in this dynamic inhibition experiment. And the key difference between the two cases comes from the transfer of 3-pentanol from the fracture to matrix that is much more efficient than the surfactant. And we found that the affinity to oil is an important factor for practical wettability modifier. And here I'm showing the same result, but in terms of the injected, the mass of injected chemical as x-axis. So you see non-zero y-intercept here because this figure started by the oil recovery values from the initial brine flooding. And you see this confirms the 3-pentanol efficiency in comparison to surfactant, and the difference will be more significant if we consider the cost of the chemicals. And the second set of experimental data I'm presenting here is based upon the also crude oil from Texas shale play. This oil was more dense than the previous case. Molecular weight is 240 grams per mole, and reservoir temperature in this case is 338 Kelvin. And we used a realistic injection brine available for the injection in the oil field. So initial reservoir brine is a salinity of 66,000 ppm. And this injection brine, on the other hand, is a low salinity and very rich in sulfate. So we found that this injection brine available near the oil field was actually good low salinity water for wettability alteration. So the key point in this experiment was how 3-pentanol is going to help improve oil recovery as part of this low salinity water, good low salinity water with high sulfate concentration. So we started by contact angle experiment to see the impact of this injection brine that is rich in sulfate and the 3-pentanol solution in the brine. So we found that in terms of wettability alteration, they are equivalent, meaning addition of 3-pentanol did not improve the wettability alteration by this contact angle experiment. And then we did a half and puff experiment with this injection brine and the 3-pentanol solution in the brine using Wolfkamp outcrop cores. And this table shows the mineral composition. So you see it's quite rich in calcite. And for this experiment, we made the new high temperature pressure half in the pulse cell. So we made this for cases where we do not want to make a fracture for the core plugs. For example, when we got preserved cores from actual oil reservoirs, we don't want to make a fracture, unlike previous case. So in that case, we want to have a fracture surrounding a core plug. And also, this is going to give a different flow configuration compared to the previous, the fractured core in the conventional Hassler type core holder. So we can see the impact of the contact area between fracture and matrix on oil production. So this half on the pulse cell have maximum operating pressure of 10,000 psi, and it can accommodate a core of 6-inch in length and 1.5 inch in diameter. So we put the roof camp outcrop cores inside of this half-pulse cell, and basically fracture is mimicked as a void space surrounding the core inside of this cell. So experiment consisted of first stage of reservoir brine flooding, followed by 5 cycles of half-and-puff, either low salinity brine that is sulfate rich, or sulfate rich brine, SRB, or the 3-pentanone solution in the brine. So the reservoir temperature of 338 Kelvin was set, and the pressure was changing from 61,000 psi for injection soaking time period, and also 4,100 psi for the production stage. So here's the result of oil recovery. Oil recovery factor percent OIP is shown in this y-axis, and you see 5 cycles after initial brine flooding stage for the 2 cases. So you see 3-pentanone case produced oil from the first cycle and reached the final oil recovery of 57%. And sulfate-rich brine case didn't produce oil for the first cycle, but produced from second cycle and resulted in the 15% oil recovery after the 5 cycles. So these 2 injectants are equivalent in altering wettability, as I mentioned before, but you see clear difference in oil production performance. And we are thinking the main reason for this difference comes from the mass transfer of the chemical from fracture to matrix. So the affinity of 3-pentanone to oil is playing important role in the efficient water imbusion, therefore oil production from the shale core. So here's a summary of the presentation. So 3-pentanone has been successfully tested as a wettability alteration agent, and we observed rapid wettability alteration without affecting interfacial tension of oil and water with the 3-pentanone solution in brine. And also, we observed efficient mass transfer from matrix, so from fracture to matrix is a key factor that affects the performance of 3-pentanone in oil production. And the results show that the 3-pentanone solution was more effective than the sulfate-rich low salinity water injection, and also non-ionic surfactant that we used for the cases tested. So here's the last slide of the presentation. So next steps include a half-and-puff experiment with live oil. Actually, this is being performed in this month, and we are going to have the result very soon with live oil using half-and-puff cell that I showed. And we do like to have the collaboration opportunities with oil industry for upscaling of this 3-pentanone application to field cases. And also, as I mentioned, 3-pentanone is as volatile as NC7, and it's possible to inject as part of a gaseous injection fluid, but we haven't tested. So these are the main items for the next steps. And thank you for your attention, and I would be glad to answer any questions you may have. Yes, I think so. We tested recently the surface absorption of 3-pentanone and this non-ionic surfactant I mentioned during the presentation using Sandstone and Limestone. And Yeah, so we tested the surface absorption of 3-pentanol and non-ionic surfactant using Berea Sandstone and Texas Cream Limestone. And I'm summarizing results. So 3-pentanol absorption amount is 0.1 milligram per gram of rock with Texas Cream Limestone, and 0.15 milligram per gram of rock for Berea Sandstone. So they are both much smaller than the values observed with non-ionic surfactant for both cases. One question is what are the disadvantages of using 3-pentanol? So disadvantages, I think so. Basically, the 3-pentanol has not been tested in the oil field. I think so. We have questions about upscaling, and one of them was what's the optimum concentration of 3-pentanol. And we have studied several different cases for that question, and then we found that 1% is a good number for several different cases. But I think all depends on application conditions, and also we'd like to test the 3-pentanol process with a larger scale so that we can see the impact of the compressibility of fluids in half and puff experiment. So that's also like a major uncertainties. So how fluid compressibility is going to affect oil production along with wettability alteration by 3-pentanol. So they are not the disadvantages basically, but there are of course uncertainties when considering upscaling. So it's a really good question. Thank you. Yeah, I think yeah, optimization question. Yeah, I mentioned that 1% is a good number for several different cases we have tested. Question: how did you correct for oil volume to 3-pentanol in the produced outputs? So we measure the concentration of 3-pentanol using NMR, and for each vials from effluent. So that's how we corrected the oil production data for the solubility of 3-pentanol. So more questions about how about upscaling to field pilot test. So that's really what we want to work with the oil industry, and yeah, we are looking forward to such an opportunity with the oil company actually. So another question. So could you please comment what the main driving mechanism for the mass transfer between the fracture matrix, advection, diffusion, spontaneous imbibition? Within this experimental like a setup, because of this small scale, I think the main driving force was coming from the capillary forces, along with some diffusion advection mechanism. And I think in the field scale, we expect more driving force from the convection. So we still do not know how the mass transfer is going to behave in a larger scale. So does the wettability modifier work better in sandstone or limestones? What type of formation would you test first in the field? So I think the impact of wettability modifier is expected to be more significant in oil wet matrix. So in that sense, I think the calcite rich formation will be maybe reasonable targets for this. And we haven't tested the 3-pentanol for sandstone yet. And it's because of the sponsoring companies, and certainly we are interested in testing this for Sandstone too. Are there limitations to implement the 3-pentanone brine injection, such as unfavorable conditions hindering its performance? So I thought first that if brine by itself can change wettability, maybe 3-pentanone addition wouldn't play an important role. So that was actually the reason why we tested the 3-pentanone solution in this low salinity water that is naturally sulfate rich. But the result shows that the 3-pentanone is still very important to add in comparison to this low salinity water that already contain the sulfate as wettability modifier. So I think the changing rock surface to less oil wet is one factor, but also another factor that is important for application is the rapid mass transfer. And I believe it's coming from the strong affinity of 3-pentanone to oil that is residing in the matrix. So another question, would you recommend adding 3-pentanone during the hydraulic fracturing operations to enhance oil recovery from the well start? I certainly say yes, in order to make the greater oil production response at the early stage of the well production. How do you think 3-pentanone injection in gaseous form would differ in performance? Yeah, that's a really good question. We haven't tested, and we really like to test it with practical operating conditions with the oil companies' support. So it's possible to inject it as a part of natural gas or CO2, and as a wettability alteration agent and also miscible agent. As I said, it's miscible with oil, and in terms of vapor pressure, it's like a C7. And are there any limitation in temperature? No, I think the solubility of 3-pentanone in brine tend to be smaller at the higher temperature, but the concentration of 3-pentanone as a wettability modifier is roughly 1 weight%. And in many reservoir temperature situations, I think it's that the 3-pentanone solubility wouldn't be an issue. So another question, can you comment on the effect of injection rate on the transfer of 3-pentanone to oil in the matrix? Effect of injection rate. So I think injection rate didn't affect the performance of 3-pentanone in some previous cases, because the oil production by enhanced water inhibition wasn't like directly affected by convective flow. So another question, what is the cost of a chemical? How much volume will be typically needed in the field, and what with the cost? So 3-pentanone cost is roughly 50 cents per pound from some source of information, and required amount of volume. I think I was thinking at least we need the volume to fill the fracture, and but I think it's a part of upscaling questions, and would like to address with the more support from oil industry. Does oil recovery show a linear behavior as a function of square root of time when using wettability modifiers? This behavior is seen in conventional infusion test at the early time. Yes, I think we haven't analyzed oil production from analytical equations yet. I think I would definitely like to work on that question using experimental data. What's the solubility of 3-pentanol in CO2 or natural gas as compared to 3-pentanol in brine? We haven't studied the details of phase behavior of 3-pentanol hydrocarbon mixtures yet, and actually literature is also non-existent on that. So that will be part of the studies, fundamental part of the studies we would like to work on toward the gaseous 3-pentanol application. So thank you so much for your question. As I said, we are very much interested in working more on the questions, especially for upscaling of the process, and I'd like to hear from you if you're interested in working on this 3-pentanol with your field data, field sample. And as I mentioned earlier, this formate is also promising wettability modifier. And as I said before briefly, we can view this as a way to store CO2 in a geological formation as a part of water flooding. And we'll like to update you for the coming webinar in July. So that's all for today. And thank you so much for your attending.